Let's now talk about order of growth in detail. So our main task is this. We are given a programming problem and we are given multiple solutions. We need to figure out which solution is more efficient. And what do we do to figure that out? We find out time taken by all the solutions. We write a polynomial and then we see order of growth of every time taken, and which one is having the least order of growth. We say this algorithm is efficient. So let's now understand what do we mean by least order of growth, what do we mean by higher order of growth, how do we compare order of growth of two algorithms. So a function fn is said to be having higher order of growth or said to be growing faster than gn if this is true, or in other words this is true. So they both mean the same thing. What have we written here? We have written gn divided by fn, n tends to infinite is 0. See, gn and fn are the time takens, right? They are time takens of two different algorithms to solve the same problem. And if fn is growing faster, if fn is having more order of growth, then the algorithm whose time taken is represented by fn is a bad algorithm, right? Gn is a better algorithm because it's growing slower in terms of input size. If you take a closer look at these expressions, we are talking about n tends to infinite. That's what we talk about when we analyze algorithms. We always talk about large value of n, and to be mathematically true, we talk about n tends to infinite. You might be wondering that this might not give you correct idea in practical sense, right? For example, if there is a function fn whose value is n plus 1 and there's a function gn whose value is 1000. I'm taking the same examples that we took in the previous video, right? Let's say not only machine regions, the constants in the algorithms are higher, right? That's why you have 1000 value here and you have n plus 1 value here. Now, the order of growth of fn is definitely more because it's growing linearly in terms of input size and it's constant. So we are saying fn is a bad algorithm. The algorithm whose time taken is fn is a bad algorithm. But if user never provides an input less than 999, see, after 999 this value is going to be definitely higher. We have seen this in the previous video. But if user never provides a value more than 999, then this algorithm is going to take less time, right? So it might not be perfect practically, but that's how asymptotic analysis is done. We always talk about n tends to infinite. We do not care about the large constants, large values. We always care about n tends to infinite. And that's the reason this asymptotic analysis works, because when you talk about n tends to infinite, the order of growth is the thing that matters. Other things just go away because n is infinite, right? One more thing that we have already discussed in the previous video, the value of n represents size of input. So it must be greater than or equal to 0. fn and gn, they represent time taken by two algorithms. So they should also be greater than or equal to 0. We saw in the previous video that we talk about only one quadrant. Here is an example. We are going to use this example to show that fn is having higher order of growth than gn. And you can observe it, right? Fn is quadratic and it's linear. But we are going to use this expression, we are going to show this expression with these values. So what I do is, I do gn divided by fn. Gn is 2n plus 5 and fn is n square plus n plus 6. Now what I do is, I divide both the sides, denominator and numerator, by n square, the highest growing term. So what I get here is, I get 2 by n, right? And I get 5 by n square. And here I get 1 plus 1 by n plus 6 by n square. When n tends to infinite, this value is going to become 0, right? Because n is at the bottom, right? This also is going to become 0, this is also going to become 0, this is also going to become 0. So we have 0 plus 0 divided by 1 plus 0 plus 0. So we have 0 divided by 1, which is 0. And that's what we wrote earlier, right? If gn divided by fn is 0, then fn is said to be growing faster. And that's what we can notice also here. Let's now see a direct way to compare orders of growth of two algorithms. We can find orders of growth and compare them also. So what is the way? The method says that ignore lower order terms and ignore the constant of the leading term. So let's see these examples. If we have, say, function fn representing time taken by an algorithm, and say the value of fn is 2n square plus n plus 6. What we can do is, we can ignore the lower order terms, 6 and n, and we can ignore the constant of the leading term. This is the leading term and we ignore its constant too. So order of growth is the remaining thing, which is n square, right? Let's now see this example. We ignore the lower order term, constant is lower than linear, right? We ignore it and we ignore 100, which is the constant of leading term. So we get the value, remaining thing is n. So order of growth of this function is n square, which is quadratic. Order of growth of this function is n, which is linear. Now, when you are given multiple terms in an expression, how do you decide which one is leading, which one is not leading, which one is growing slower? For that, we can always use the basic mathematics. We can remember this thing, that constant is the slowest growing term. It doesn't grow at all, right? It's a constant, right? Log n grows, but grows very slow. Log n grows faster than log n, right? So these greater than signs represent order of growth being greater. n raised to the power 1 by 3 grows faster than log n, right? But slower than n raised to the power half, then n square, then n cube, then n4, then 2 raised to the power n, then n raised to the power n, right? So this is this is the sequence that we must remember when we are comparing two terms, or when we are comparing final orders of growth. See, final order of growth are going to be single terms only, right? It's going to be either this term, or maybe a combination of two terms like n into log n, right? But it's going to be a single term. Now, how do we decide which is having a higher order of growth? We can simply use this, right? This sequence. For example, say you have one algorithm whose order of growth is n log n, and another algorithm whose order of growth is n. How do you decide which one is better? You can cancel n and n, and you can see it's a constant. Remaining thing is constant. Here you will have log n. So this is definitely a higher order of growth, right? And log n is higher. So this is the idea we use. We ignore the lower order terms, ignore the constant of the leading term. Whatever we get, which is basically the leading term only, right? The n part of the leading term. That's what is the order of growth, right? And here we get n. Now to compare these two order of growths, which algorithm is having, we again use this thing. We use this sequence to decide which term is leading, and to again compare final order of growth also. Here are exercise questions for you. Please take a closer look at both of these questions. The question 1 has two functions fn and gn. The question 2 also has two functions. You need to find out orders of growth of both the functions, and you need to tell which one is having higher order of growth. So let's use the direct way to do it. We ignore the lower order term. We ignore the constant. See, in both the questions, these values C1, C2, C3, C4, C5, C6, these are all constants, right? So we ignore the lower order term, C2. We ignore the constant. So our order of growth of Fn is log n, right? And order of growth of Gn, we ignore the lower order term. Log n is lower growing term than n, right? Way behind n. So ignore it. We ignore the constant of leading terms. For Gn, it is n. Right? Now, which one is growing faster? Gn, because n comes after log n, right? So we have Gn as higher growing term, and Gn is a bad algorithm. The algorithm whose time taken is represented by Gn is a bad algorithm, right? So let's see this example. Here we ignore the lower order terms, right? We ignore this constant, so we get the order of growth of Fn as n squared. Here again, we ignore the lower order terms. We ignore the constant. We get the order of growth of Gn as n log n. Now, if I compare these two, right, which one is having higher order of growth? See, I can cancel 1 power of n with this, and I have n here and I have log n here, right? So which one is having higher order of growth? N, right? So among n and log n, right? So we say n square. This Fn is having higher order of growth. So the algorithm whose time taken is Fn is a bad algorithm compared to the algorithm whose time taken is n log n.